Thank you very much for the introduction. So I'm of course very grateful for the organizer for letting us talk here. I really enjoyed the program so far. It was already quite fun. So today I will talk about two different data analysis methods. So it's quite useful for different applications in SPM. So it's basically looking at either a frequency domain or a time domain approach. And what I call basically either smart data, so by this I mean real-time data crunching, or big data, which would be like really fast data streaming, and then the analysis afterwards. So let me just start with a slide on Zurich Instrument Company. So we are based in Zurich. We have grown to quite a good level in the last 11 years. We are addressing actually a lot of different markets, but always in the mind of fast digital signal processing. So of course SPM is an important one, but we also have application in photonics, in MEMS, now also in quantum computing, so in other applications. So that requires a good team of scientists. Many has PhDs. And as we expand, we have actually an office in China, in US. I'm actually based in France. We have also offices now in Italy and Korea, to be as close as possible to our customers. So that will be the outline of my talk. So basically, to address the difference between data crunching and data streaming. Of course, the point is to be as quantitative as possible and not just have relative or nice images. And that basically corresponds to resonance enhancement technique and closed loop techniques. So when you can count only on a few frequencies, or some sort of band excitation method, or like big data acquisition. So I know that I only have 20 minutes, so I have to go to the point, but let's just look at an eye view of AFM. So basically it's a mechanical amplifier where you can get both a DC and an AC contribution, and because it behaves like a very nice, sinusoidal or harmonic oscillator, lock-in works quite well, because then you have all the information that you need, which is the amplitude and the phase, and you have a fixed frequency and excitation. So that's the way to look at the AFM part for a single frequency. And actually, there are because it is well behaved, it's also not so difficult to get the math out of this. So you can derive three basic AFM equations, which has been really nicely summarized in this paper from Hagen Songen in Angelika Kühlner's group. So what is amazing is that you just need basically three observables. So basically the static deflection, the amplitude and phase that you would get from a lock-in, and then the two parameters that are defined by the user, which is the drive force, which has a certain frequency and force, and amplitude. Yeah. And of course, then you have many variations of the typical type of mode you want, depending on whether some parameter can vary or are fixed. And there are either open and closed loop. And actually, all of these modes can be just derived. So if you check this paper, and the only approximation is that you have a linear approximation. So basically, that you follow this sine wave response. But when you actually come now when you actually bring the tip to the sample, the first thing that you observe, so this is real measurement, so actually in vacuum, so it's actually already a well-defined system, but you see right away that you have a bunch of peaks appearing, so that corresponds to the nonlinearity, because of course you have a nice sine wave, but any small variation from this from the tip sample interaction, then the sinusoidal is going to be distorted, and that generates harmonic distortion, or mixing to different modes. And so that's also a way to illustrate let's say, big data or data crunching, because this is an FFT, which has actually can go to quite a high frequency, and then you can end up with a lot of points. So something like a gigabyte of data. And of course, either you take the brute force approach and you just want to get the whole data set, or you want to, if you consider that maybe only 10 of these peaks are enough, then you can just measure the amplitude of phase of this point and this point and this point, etc. And that corresponds to basically the demodulated output that you can get as a function of time. And this, of course, is much more reduced now. We are talking about just a few kilobytes, and that's what makes the real-time images so much easier. Of course, if the frequency itself is changing and you have a fixed frequency, then you may have some variation. So that's why there are many other techniques for this. And actually, so when we look at this either full data acquisition or data crunching method, I have plotted this. So basically, we can look at the demodulation bandwidth speed versus the digitizing speed. But you could also look at the frequency domain versus time domain. And so the idea is that so if you can either crunch the data and do the computation quite fast, but then you will to a certain demodulation speed, or you can acquire everything over the full time window that you are available. And so in that regard, we have three classes of instruments. So from 500 or 5 megahertz input range up to 600. And all three instruments can be quite useful for AFM application, depending on what you are really looking at. If it's more time resolved, or if you want to do fast images. And but some of the key parameters, key specs are written here. So on the best case, you can actually stream, so one demodulated transfer rate that corresponds to one amplitude and one phase. So that can be up to 800,000 amplitudes per second. So that's already quite a lot. But if you are just in a triggered fashion, so if you do it only when you have a trigger, it can be higher. And then if you want to digitize, because you have this so we can digitize 1.8 gigasample, but then we can have a sustainable rate at 56 megasample, and that means that you can have a bandwidth of about 20 megahertz if you consider Nyquist, which is of course way enough information for a typical AFM application. So that was for the overall information that we can get from the instrument, and let me focus on that frequency tracking concept and why it is actually quite important. Because many people tend to so everybody likes resonance enhancement, because of course, I mean, if you look at the signal here, you have kind of a few milliamp, and then if you go on that value, it's multiplied sometimes by even 1,000 or more. So of course, everybody wants to sit where you get the highest sensitivity, especially now with nanotechnology, quantum application. I mean, everything gets weaker and weaker, and of course, you need to enhance the signal. But now, if now this is shifting because of some tip sample interaction or some other cases, then the value changes. And that also changes the transfer function. So that means that it is not so much quantitative anymore. And so that's why to be able to really track the frequency guarantees that you are always at the resonance, and therefore always have a constant transfer function. So this is implemented by using just a local oscillator that is both phase locked on one hand, and at the same time the same oscillator is shared at a 90-degree phase shift. That's exactly what a lock-in does to the amplitude. And the fact that you have locked the phase with this PLL guarantees that basically you have here 90 degrees phase difference, and therefore you can have really an in-phase and in-quadrature component, and that's really orthogonal. So that means that whatever information you are going to measure on one information channel will be orthogonal to the one you will measure on the other one. And actually that was, so that's why you can end up with like conservative forces, so that would be on the frequency shift, and dissipative forces on the amplitude, which correspond to the amount of energy you have to put into the system. So, and once you have defined this, then you can even go a little bit further. So for instance, so now that would be the mechanical phase, but you could also have an electrostatic phase where you can project it onto the dissipation channel. That's called actually dissipation Kelvin probe. And actually, even what Lucas shows this morning is dissipation is also carries a lot of information, and it's actually nice to have it orthogonal because then you can distinguish the contribution differently. Yeah. And just to clarify, so basically the reason why people have to have a phase lock first is because here you have a nice slope. If you would lock the amplitude here, it would change slope. So of course this would be unstable. So you can only lock the amplitude after the phase is locked. Yeah. And of course, the story behind this is that you need to have, you need to understand exactly what happened between your input and your output. So you have different models that you can apply. So the most obvious one for a resonator, you have a resonator amplitude, resonator frequency. So that's the one that has so the gains, so this you can all determine from an open loop transfer function, so that means just making a sweep, so you can know the response. So that will be the ratio between your input and your output. But therefore you can, but if you don't necessarily know that it has, you can have other models, and that's actually very versatile because you can use it for Kelvin probe, for DFRT, for like other contact resonance mode, or even some interferometric cavity feedback, because in the end you don't care, you can be quantitative and you can measure the parameters and then apply such a filter. Yeah. So once you define a nice resonance, so typically you can start to make a little bit more complex experiment, like adding some additional modulation. So that's a very typical one for Kelvin probe. So basically you have you mechanically drive so that your carrier, so that the frequency at which your resonance is locked. But then if you now start to apply some AC modulation, you will see these psi bands appear. So this is again real data. So that's basically the FFT of the lock-in output. And so and in this case, that's a motivation for having several demodulators, because here you need at least 5 to measure the to measure the amplitude and phase of each of these peaks. And then of course you can apply feedback, and then when you apply a feedback, then you see that you can compensate for the electrostatic contribution, and therefore you don't have the omega component anymore, but you still have the 2 omega component that remains, because this is only capacitive, which you can also measure at the same time. Or some people even can make some feedback on that too. So that's this typical example on Kelvin probe. But there are many variations. So of course you have AM Kelvin probe, which is also a non-resonant, technique. So that's why for good resolution people tend to prefer FM. But I think some cases it's quite slow because the modulation is quite slow, and that's why now people are moving towards either dissipation Kelvin probe, because therefore you can actually modulate at the cantilever frequency if you project this electrostatic phase to the dissipation, or you can do some time or electrical pump probe from doing some time resolution. Yeah, but I'm not going to go too much into these details because I want to keep on schedule. Sorry. I will have another example of a contact resonance tracking method. So that's for PFM, because there are many people in this community doing this. So typically, if you would look at this, you could think this is a phase, and it's basically a way of going back to a PLL mode, except that you don't use the phase, you use the amplitude, because the phase can flip. So for this, you just make the difference of the 2 amplitude, and when you plot this difference, that corresponds to this. So here you are in a very nice regime where you can have, you can define a set point, you can know your slope, therefore your gain, and of course, because this is linear, then you can apply a very nice PI feedback, and that works for tracking the resonance. Yeah, and we will actually have tutorials on that too. So typically you again need several demodulators with a certain modulation, but now it's not a frequency modulated technique, it's an amplitude modulated technique. So you basically make the computation directly internally, digitally, then you will act on the oscillator of the carrier, so the one in the middle, and then you're not limited to 1 or 2 or 3, but actually you could do a lot of images at the same time. And this is useful for standard PFM, let's say for out-of-plane component, but you can do it also for in-plane components, so you can have 2 images at the same time. You can record also the images digitally, not necessarily have it on auxiliary output. So that's just an example where you have a sawtooth corresponding to your forward and backward, and now you trigger, and then every line will be corresponding to the frequency shift or to the amplitude that you get. And so this you can do for in-plane and out-of-plane at the same time, but another way of doing it is that if you now, PFM and contact mode resonance technique are often quite complex, and sometimes you have contribution from ionics, from thermal expansion, so from, of course, piezo response, piezoelasticity, I don't know. So here it's a nice paper from a customer in Washington, in Seattle, where they were discriminating the thermal contribution, the ionic contribution, just by looking at some omega and 2 omega and 4 omega component. And in this case, so they could also look at the contact resonance at this omega and at this 4 omega simultaneously. So therefore, it was getting all the information at the same time, and therefore you could plot. So that kind of a multi-frequency technique where you could plot the 2 omega contribution that was related to the ionic, and I think the 4 omega contribution that was to thermal expansion. And that comes with a single scan. Okay, so that was for, let's say, the data crunching approach, some sort of multi-frequency approach that you can do. But there can be application for which you want to get the full signal acquisition. And in this case, so you still start from your mechanical amplifiers that you want to convolute the tip with a sample, but instead of applying a single sine wave or a multiple sine wave, we can apply a complete chip or a type of burst or other type of techniques that you can even make a reverse FFT to find the one that you want, and then stream the data. So now it's basically is not x-axis, it's a time axis. Of course, you can relate the time to your x component or to your xy component, but then you can trigger this for every line, and then you can reconstruct offline. So in this case, you will not do an amplitude or phase measurement. You will just stream the data and then apply different filters. So Zurich instrument would actually help you to get up to that point. So basically to put the matrix in the right format. So it's already getting there. Yeah. So of course, so once you have everything nicely triggered and you have all the data that is aligned, then you can start to do some matrix diagonalization. So basically looking at the different eigenmodes here, and so finding the principal component or the one that has the biggest contribution. And then you can apply either different filtering or like go back to simple harmonic oscillator or the one. Then of course you end up with many different images that you can get. Concretely, the way we do it, and we have this also outside with our UHF, is that you excite the complete band. So it's actually that's just from output to input, then you have a flat band. So if now you apply if you have your cantilever inside or your system, you can measure the frequency response, but over the complete over the wide band. And actually here, this is not a sweeper, this is a scope. So basically it happened just like that, just a scope shot, and that because it's synchronized with the chip, and it can be leakage free, so that means that you use the same amount of data for the generation and for the detection. So you can really link the two. So of course then you have to link it to your scan generation, and then you can reconstruct images. And so this is, well, I like to show this because this really shows how the tip trajectory can be quite complicated. Normally this, we expect to be a certain just a sine wave, but then of course, depending on the tip sample interaction, then it changes the shape quite a lot. But so that would be an example for one image, and of course you could do it for the different eigenvectors, but this is a post-data processing, and that depends on the data analysis method of the researcher. Yeah. So I will stop here. So the point is was to really show some different approach between like this data crunching. So let's say if you have a well-behaved tip trajectory, or that you know that you can model your system is a bunch of frequencies, but limited to a reasonable amount. But if you want to go further and you want to go deeper analysis, with the same instrument, basically, you can also get the full data acquisition and then do this independently. The nice thing is that it's platform independent, so you could hook it up to your Park system, you could hook it up to whatever platform you have in your lab, and that's very portable and flexible. So thank you very much for your attention.